We've come to the last section of Chapter 8, which is Section 11, and this is predicting which mechanism is likely to happen, SN1, SN2, E1, or E2. So we'll typically find that if you have a good nucleophile that's a weak base, that's going to tend to favor substitution over elimination. Examples of this are going to be things like iodide and bromide, hydrogen sulfide ion, the cyanide ion, and the acetate ion. So these are all pretty weak bases. In fact, some of them are just not very good bases at all, and but they are pretty good nucleophiles. So here's an example. Iodide comes in and does a reaction and does substitution. This is going to be strictly an SN2 mechanism because of the primary alkyl halide. If we have a bulky base, we'll find that the bulky bases tend to favor elimination. So bulky non-nucleophilic bases will favor the elimination over substitution. So if we were to do this reaction with something like hydroxide, that would be a strong base, but it's also a pretty good nucleophile just because it's a good nucleophile. However, when we pick something like potassium tert-butoxide, it is a strong sterically hindered base, which makes it not nucleophilic. It doesn't act as a good nucleophile because of all the bulk around it. So it's just too big, too sterically hindered for it to attack the carbon. However, it is able to deprotonate that small proton and do the reaction. So strong sterically hindered bases like potassium tert-butoxide. We'll also find DBU and DBN, which we talked about earlier in this chapter. Those are very good at doing E2 eliminations as well. When we have tertiary alkyl halides, well, tertiary alkyl halides automatically eliminate the SN2 possibility because of steric hindrance. However, it is possible to do an E2 mechanism if you have a strong base. So it is possible to do elimination. And if you have a weak nucleophile like water or an alcohol, that also acts as the solvent, then we will find that those things tend to give us a mixture of SN1 and E1 products. So here, for tertiary alkyl halides, strong base is going to give us E2. Weak base as a nucleophile give us SN1 and E1. If we have a primary alkyl halide, that automatically eliminates the possibility for doing the carbocation mechanism. So with strong nucleophiles, we'll get substitution. So if we have a strong nucleophile like hydroxide, we'll get substitution. If we want to do elimination on a primary alkyl halide, we need to use a strong sterically hindered bulky base like potassium tert-butoxide, and we can get the E2 product. For secondary alkyl halides, everything is on the table. And so this is where we have to pick what it is that we're trying to do. If you have a strong base and strong nucleophile, so things that count as both strong bases and nucleophiles, hydroxide is a great example, and you do that with a secondary alkyl halide, you're likely to get a mixture of SN2 and E2 products. And that could be kind of tricky. With strong bulky bases, the sterically hindered bases like potassium tert-butoxide, you can eliminate the substitution product and just get the elimination product. And that's convenient because that allows you to get rid of this possibility. And then if you have a weak nucleophile or a weak base, then you can get a mixture of SN1 and E1 products. This is part of why we just don't like doing SN1 and E1 as much as we like doing the SN2 and E2. Because here we end up getting a mixture of products, and it's difficult to control how much of these that we get. And now for solvent effects, As we've seen before, the second order mechanisms will be favored by polar aprotic solvents. The reason for this is that they don't solvate anions well, and that allows strong nucleophiles and strong bases to be more effective. Polar protic solvents, on the other hand, will tend to favor the SN1 and E1 mechanisms. So water, alcohols, things like that will tend to favor the SN1 and E1. Those are really good at solvating the ionic intermediates better. So we're going to look at 53 and 54 on the in-class assignment. Right, so here is 53, and for this one, the question is for which reaction mechanisms, SN1, SN2, E1, and E2, are each of the following statements true? A statement may be true for one or more or all of the reactions. So we want to list what things will be either favored or that makes the statement true about each of these. So the mechanism involves a carbocation intermediate. Well, the carbocation intermediate, we only see that with our first order reaction mechanisms, so SN1 and E1. Both of those have the carbocation intermediate. SN2 and E2 are concerted reactions and will not see the carbocation. A mechanism has two steps. Again, that first step is the production of a carbocation intermediate, so SN1 and E1 will have two steps. The reaction rate increases with better leaving groups. Well, this is one of those cases where a better leaving group is going to help the rate of all of the reactions. So this is going to be true of SN1, SN2, E1, and E2. All right, so better leaving groups improve all of our reactions. The reaction rate increases when the solvent is changed from methanol to, this is DMSO, dimethyl sulfoxide. So methanol is a polar protic solvent, and DMSO is a polar aprotic solvent. So if we increase the rate when we change it to a polar aprotic solvent, that is going to be true for our second order mechanisms for the SN2 and E2. All right, the reaction rate depends on the concentration of the alkyl halide only. All right, well, the things where it's dependent on the concentration of the alkyl halide only, those are first order mechanisms, and so that is going to include SN1 and E1. All right, the mechanism is concerted. Well, that's going to be exactly the opposite of a two-step reaction. It's going to be just a one-step reaction. So that's going to be the second order reaction mechanisms, the SN2 and E2. All right, the reaction of ethyl bromide and sodium hydroxide occurs by this mechanism. So this is a primary alkyl halide. Primary alkyl halide eliminates the possibility for the carbocation intermediate in the first order, so we can't have SN1 and E1. And sodium hydroxide, that is a strong nucleophile. It's also a strong base, but because this is a primary alkyl halide, this is going to be preferentially an SN2 reaction. If we had had a sterically hindered base, something like potassium tert-butoxide, we could have favored the E2 product, but it is a strong base, but it's going to be a good nucleophile as well, so SN2 is our likely reaction here. Racemization at stereogenic centers occurs. All right, so racemization occurs when you start with an sp3 hybridized carbon and you end with an sp3 hybridized carbon, and when you have a carbocation intermediate. Well, that is only going to occur with an SN1 reaction. With an E1, we do get that carbocation intermediate, but then we eliminate, and so the product is no longer sp3 hybridized and can't be a stereogenic center. So that won't be racemization. It will eliminate the stereogenic center, but only the SN1 will give racemization. All right. Tertiary alkyl halides react faster than secondary or primary alkyl halides. Well, this is going to be true for any of the first order reactions, the SN1 and E1, because they have carbocation intermediates and the tertiary goes faster. But we'll also find that this is true for the E2 mechanism. So this will be true for SN1, E1, and E2, not the SN2. SN2, the tertiary alkyl halides are going to be prohibited because of steric hindrance. So SN1, E1, and E2. And then finally, this reaction follows a second order rate equation. Well, of course, it's right there in the name of these. The 2 and the 1. 1 means first order and 2 means second order. So this is going to be true for SN2 and E2. All right, so let's look at number 54 on the in-class assignment and determine, based on the information that we have, determine what is going on. So here we've got a primary alkyl halide. Let's identify what's possible here. So this is a primary alkyl halide that automatically eliminates the SN1 and E1 as possibilities. We have, so really our only possibilities here are going to be SN2 and E2. However, you'll see here that we've got a strong sterically hindered base. So, so it's non-nucleophilic. So I'm going to put strong sterically hindered. All right, and that means that this has to go by an E2 mechanism. Has to be an E2. So we ruled out SN1 and E1 because it's primary alkyl halide. They can't form carbocations. And we can rule out SN2 because that is not nucleophilic. So that means our product is simply going to be the elimination product, and we'll eliminate between carbon 1 and carbon 2 there. So 1, 2, 3, 4, 5. That methyl will still be there, but we will get the elimination product. Okay, here we've got a primary alkyl halide. Again, primary alkyl halides eliminate the possibility of the first order reaction mechanisms. So we can, it's either going to be SN2 or E2. Here we've got a good nucleophile. It is a strong base, but it's not a sterically hindered base. And so strong bases that are good nucleophiles are going to preferentially give us the substitution product. So 1, 2. If we had chosen a sterically hindered base, then we would have more likely gotten the elimination reaction. But here we're going to get almost exclusively the substitution product. So I'm going to put S in 2 there. All right. Anytime you see a really strong base and you see 2 equivalents, that's going to be a double elimination. And we should, particularly if you have a dihalide, we're going to have a double elimination, and we should form an alkene. That elimination is going to be by E2. So CH3, and then C, carbon triple bond, hydrogen. So we would get that alkyne as our product. And so, yeah, E2 mechanism, we'll do it twice. And this, just as a reminder, that is a geminal dihalide. All right. Anytime we have dihalides, we are looking at doing two eliminations and forming an alkyne. All right, DBU. DBU is a strong sterically hindered base. Here we've got a primary alkyl halide, and this is sterically hindered. And so with the sterically hindered base, that is going to give us an E2 mechanism. And with the E2 mechanism, we should get elimination and form that exocyclic alkene. So we will get that as our product. Okay, here we've got a secondary alkyl halide. Let's go ahead and label that as secondary. That means everything's on the table. We just have to look at what our base is, our base/nucleophile. This is a strong sterically hindered base because it's tert butoxide, and that strong sterically hindered base is going to favor the E2 elimination. We do see that there are two places, there are two beta hydrogens that we could potentially eliminate, and that means that we will have two products. And I will draw both of those products. Now, without the stereochemistry represented here, indicating whether this is cis or trans, we don't know if one of these possibilities would be eliminated. So I'm just going to draw both of them, and we'll leave it there. All right, and so that will give us two products. If both are technically possible, this would be our major product because it is a more substituted alkene. All right, next we've got a tertiary alkyl halide. Tertiary is it's going to favor SN1 and E1, but it's also possible to do an elimination, an E2 elimination with tertiary. So we have to see what our base/nucleophile is going to be. Here we've got a weak base/nucleophile, and with a weak base nucleophile, that means that we are probably going to do the SN1 and E1. We'll get some of each of those. We are not going to get SN2, of course, because it's tertiary, and E2 is going to require a strong base, and this just does not qualify as a strong base. So looking at what our products can be, let's do the substitution product first. Because we've got a neutral thing, we would get positive and then deprotonate. So we'll have CH2, CH3, and then O, CH2, CH3. So that would be our substitution product, which is an ether. And then we have two possibilities for an elimination product. One is going to be the more substituted CH2, CH3, and then the other so CH and then CH3. So would be this exocyclic alkene. All right. From those, this one is probably going to be favored, although both of these are tertiary alkene, or not tertiary, but tri-substituted alkenes. But generally speaking, if you've got an endocyclic, which means the alkene is part of the ring, versus an exocyclic where the alkene is coming away from the ring, that the endocyclic is usually major. That is not something I'm going to test you on at this point, but it is kind of interesting. Anyway, that's a lot of different things, and part of why we don't love doing SN1 and E1 for complicated molecules. All right, so here we have a vicinal dihalide. So vicinal dihalide. All right, and I just realized I spelled vicinal wrong. It's with an A-L, not a Y-L there. All right, so we've got a vicinal dihalide, and we're going to do a double elimination between these two. We will not eliminate over here. We're going to eliminate between these two and form an alkene. So we've got this strong base, so this is going to be E2, but it's going to be a double E2 reaction. And so we'll get CH3, 2, CH, carbon, triple bond, carbon, hydrogen. So we will eliminate twice across that carbon-carbon double bond. All right, here, this is a geminal dihalide. So geminal dihalide. And we've got two equivalents of our strong sterically hindered base. And so this is definitely going to be the 2 times the E2 reaction. There are no beta hydrogens on this carbon, so we will only do the elimination between these 2 carbons. So we should expect that tert-butyl group, carbon, triple bond, carbon, hydrogen. And that would be our only product. All right, you'll notice here that we've got a secondary alkyl halide. We'll go ahead and label that. Secondary means everything's on the table, and we need to look at the base/nucleophile and the solvent. You'll notice here we've got a weak base/nucleophile, and presumably the ethanol is acting as the solvent as well. So we will find that this is going to be a combination of SN1 and E1. For the SN1, we would get the ether. So there's our butane, and then O. So we would get that ether. And again, there's a deprotonation step that happens right before the end. And then for the E1, we would get a combination of our products. So we would get that di-substituted alkene and a mono-substituted alkene. On top of that, we would probably get some of the cis-2-butene as in addition to the trans-2-butene. So this one's a hot mess. There's a lot of stuff going on there. All right, here we've got a tertiary alkyl halide that's going to tend to favor SN1, E1, and E2. However, we've got a weak base/nucleophile. So this, like that one that was right above it, is going to be SN1 and E1 exclusively. We will not get any of the E2 mechanism. However, that won't really affect what our products will be. So when we substitute on that chlorine, we will end up with the alcohol. All right, and again, we do the substitution, and then there's a subsequent deprotonation that would occur. So we would get that alcohol. We would get the alkene, and since there's 2 different types of beta hydrogens, these 2 are the same, but then this one is different. We get that one as a possibility. All right. There would be a stereoisomer of this one, but that is not our primary concern. All right, so that is the end of this section, also the end of this chapter, so the end of chapter 8. This is kind of a doozy of a chapter, so make sure that you go through. Fortunately, there's a lot of things that we learned in chapter 7 that will help us in chapter 8. So study it hard and stay tuned for chapter 9.